Hi, and welcome back to another lecture. We're going to talk about section 6.4 today, which is diving deeper into factoring trinomials, giving us a little bit more practice and rounding out our rules. As you might have remembered from the previous lessons, we've talked about factoring using a GCF, or a greatest common factor. This will be the first step that you take every single time that you're factoring a polynomial. Look to see if there is something common between all the terms. You have the next step and the next few steps actually digressing based off of the type of polynomial you're working with. So if you have a 4-term polynomial, you can factor by grouping. If you have a 3-term polynomial, you can use one of 3 different methods, either the box method, which helps you to organize your thoughts, the guess and check, which is really just doing the same thing as the box, but doing it mentally, and then you have the AC method. The AC method is a little bit more involved, but it works for a lot of those terms where the A value, or the leading coefficient of the polynomial, is larger than 3, typically. Now, that being said, we're going to just do a quick recap. You might have seen a couple of these problems before, but as we dive into 6.4, this is a good refresher point. So we are going to go into our first example. I have 3x squared plus 11x plus 6. A couple different choices here. The first is, do you have a GCF? No. Is it a 4-term polynomial? No. Is it a 3-term polynomial? Yes. That means I can use box, guess and check, or AC. The preference is really up to you. However, for the purpose of this particular video, I will use the AC method just to give us a refresher. So the AC method, I take my A term and my C term, multiply them. That gives me 3 times 6, which is 18. And now I'm looking at factor pairs of 18 that would give me 11. So I'm looking at, in particular, 2 and 9. Using my 2 and 9, I will split up this 11x into 2x and 9x. Notice I did not add signs initially. I'm going to go back and check myself. How do I get from 2x and 9x to a positive 11x? Well, both of those need to be positive. All right, at this point, I'm going to play a little fruit ninja and slice this in half. I see that I have x in common here. That leaves me 3x plus 2 left over. I see I have a 3 in common over here, and I don't want to change my sign because this is already positive. So plus, and I'm going to take a 3 out. That leaves me 3x plus 2 left over. Pulling out my 3x plus 2, I am left with x plus 3. And that's your factored form. Let's take a look at this next one. So I have 8x squared minus 22x plus 5. Again, I'm going to use AC method here, but do I have a GCF? No. Is it 4 terms? No. Is it 3 terms? Yes, and that's why I can use my AC method. So we're going to jump right into it. 8 times 5 is 40. Factor pairs of 40, that might give me 22. 2 and 20 are kind of shouting at me there. I'm going to use 8x squared, 2x, 20x plus 5. Again, notice I did not put signs in here when I split up that 22. I know I need a negative 22. How do I get it from here? Both of those have to be negative. All right, I'm going to play some Fruit Ninja. I can pull out a 2x over on this side. That leaves me 4x minus 1. I want a sign change here, so I'm going to pull out a negative. That leaves a common term of 5 between these, so I can pull out a 5. That leaves me a 4x minus 1. Remember, you had a sign change. I can then pull out my 4x minus 1. You have 2x minus 5 left over. And that is your factored form yet again. Again, this is just looking at really extending our discussion on factoring. So some of these problems may be repetitive to what you've already done in your notes. However, I don't believe we've covered this problem. So this is 30x squared minus 23x plus 3. Now, go through the process. Do we have a GCF? I don't see one. Is it 4 terms? No. Is it 3 terms? Yes. Which method would you like to use? That's a personal preference. I personally will be using AC method because this lead coefficient is far greater than 3, which means I have a lot of combinations that I can use. So I'm going to take 30 times 3, which is 90. I'm going to look at some factor pairs of 90. I got a lot of them, so keep in mind you've got a lot of options here, and you have to think about what through addition and subtraction will give you 23. Let's consider. Obviously, I have 3 and 30. What else do I have? If I look at 2 and 45, 1 and 90, those are really big values, right? So what else do I have? Can 5 go into 90? Yeah, it can. How many times does 5 go into 90? Well, what you could do is obviously pop out a calculator and see if that works for you. But I'm going to just go ahead and say 5 goes into 90 18 times. Hey, 5 and 18, that gives me 23. Let's use it. Let's see what happens. This might be the pair that you want. It might not be. If it doesn't work out, keep going with your pairs. But I'm pretty certain this one's going to work out. So I have 30x squared, 5x, 18x, notice again, no sign, plus 3. How do I get a negative 23 from these two? They both got to be negative. Fruit Ninja. Now, over here, I got a 5x in common. That leaves me 6x minus 1. Over here, I want a sign change, so I'm pulling out that negative. I have 3 in common, so that's a 3 that I can pull out. I am left with 6x minus 1. Don't forget about that sign change that you pulled out. Hey, 6x minus 1, 6x minus 1, that worked out nicely. So I have 6x minus 1, and then 5x minus 3. And there's your factored form. All right, let's try this next problem. While we're on a roll here, we have 30a squared plus 5ab minus 25b squared. Okay, sorry about that small little break in the video. That being said, our next problem is 30a squared plus 5ab minus 25b squared. Now, again, going through our process of elimination here, I'm looking at my factoring rules. Do I have a GCF? Yeah, looks like 5 goes into everything. So I'm going to pull that out. Anything else? No, because they don't all have the same variable. So I'm just going to pull out a 5. Okay, so I have 6a squared plus ab minus 5b squared. And so there is my new problem. I'm going to just circle this GCF. I'm going to bring it down because I know I'm going to reference it later. All right, so I have 6a squared plus ab minus 5b squared. At this point, you could use, is it 4 terms? No. Is it 3 terms? Yeah, I could use box, guess, and check, or AC. Again, matter of preference. Now, in this particular instance, just because I'm hammering in the AC method, I'm going to use the AC. But again, matter of preference. So I'm going to say 6 times 5, which is 30. I'm looking at factor pairs that would give me 1. From 30, that's 5 and 6. So I have 6a squared, 5ab, 6ab, minus 5b squared. Now from these two, how do I get a positive ab? Well, that has to be negative, this has to be positive. That's what it looks like to me anyway. Math Ninja, I have a in common here, so that's it. I have 6a minus 5b left over. Over here, I have a b in common, and I don't want to change my sign, so plus b. And I have 6a minus 5b left over. Those match up. So I have 6a minus 5b, a plus b left over. And hey, I see an arrow, so that's a 5. Okay, very good. So at that point, we've already been able to go through our factoring process. This is a great recap from where we were last time, going through our factoring rules. Now I'm going to kind of shift into section 6.5, and I just want to show you what that looks like by comparison. So far, we've been able to do GCF factoring, we've been able to do 4 terms, we've been able to do 3 terms. So the question then becomes, how in the world do we do this? It doesn't have 4 terms, it doesn't have 3 terms, it does have a GCF, so I could pull that out. 2 goes into both of those, so that's x squared minus 25 that's left over. But then, what do I do? We need a new rule. In fact, you've already seen this rule, this definition rather. And so we're going to build on to our factoring rules. If you're dealing with a 2-term or a binomial polynomial, we're going to factor by definition. Factor by definition. I'm abbreviating definition, that's DEF. And you have a couple definitions. The first one is the difference of squares. Yes, I told you this would come back to haunt you once you learned it, and here it is. Just as a quick reminder, the difference of squares says that if I have x plus y times x minus y, conjugate values, then I get a solution through multiplication of x squared minus y squared. However, we are math ninjas. This is what we do. Wax on, wax off. You can go backwards. Now, what that means for us is I'm looking at a situation like this, where I have x squared minus y squared, or the difference of 2 perfect squares. I know that that difference of 2 perfect squares will factor by definition to this, where I have the roots, the factors, if you will, in a conjugate pair. So x squared minus 25, those are definitely perfect squares. I'm going to go ahead and put some parentheses here. I'm just going to bring this 2 down. What times what gives me x squared? X and x. What times what gives me 25 perfectly? 5 and 5, they are exactly the same. What are my signs? Positive and negative. Now, it does not matter on the order in which you write this, either x plus 5 or x minus 5, whichever one comes out first. Don't forget this 2. But I always suggest to my students that you write the negative last. And there's a very clear reason why we write the negative last, and that is because you still need to check this one to see if it continues to factor. I'll give you a great example of that. It is not currently listed on the page, but you will want to write this in. Let's say I have w to the 4th minus 1. Just to prove my point as to why we write the negative last. W to the 4th minus 1 is by definition a difference of squares problem. You could get this where it's w squared plus 1, w squared minus 1. But wait, there's more. W squared minus 1 is also a perfect square, difference of perfect squares, which means this little piece can factor down even more. You have w plus 1, w minus 1 there. this just comes down. The sum of squares, which is what you have here, does not factor. Don't even try it. So the only one that you need to always continue to check is the difference. That's why I write the subtraction in my factoring at the end. Now, that being said, this is the difference of squares. It's absolutely beautiful, so let's try some more problems. By the way, you have these definitions at the very top of your notes should you need a quick reference. So the next problem that I have is 9g squared minus 16. Perfect square, so I'm going to go ahead and factor these down. I see 3g, 3g. 16 breaks down to 4 and 4 signs, positive and negative. Can this break down more? No, it's not a difference of perfect squares. Leave it alone. All right, great. What about this next one? X cubed plus 125. Does it have a GCF? No. Is it 4 terms, 3 terms, or 2 terms? It's 2 terms. Is it a difference of squares? No, it's not even a difference. So what do? We need another definition. Let me introduce you to the sum of cubes. Now, the sum of cubes is another binomial definition. It takes a little bit of working through and a lot of practice to really get a handle on this, but the sum of cubes works like this. If I have x cubed plus y cubed, the sum of two perfect cubes, then you will always factor down like so. You have x plus y, x squared minus xy plus y squared. And you might be thinking, what? That's okay. Work through it with me. I'm going to go back and rework this definition using this problem. The perfect cube of 125 is 5, so it's 5 times 5 times 5. Now, here's how it works. Understand that your definition will come out to a binomial and a trinomial. That being said, give yourself some room. The binomial is the one that you really have to figure out. That's the hard one. How do we get it? Well, ask yourself for the first term, what times itself 3 times gives you this first term? So how do you get x cubed? X times x times x. So that's x. How do you get 125? 5 times 5 times 5. That's 5 times itself 3 times. So 5 times 5 times 5, that's going to be a 5 right here. Awesome. Now, what about the sign? The sign is always the same. So right here for the binomial, the sign is always the same. So that is a plus. That's the hard one. Now the rest is easy. The rest comes from definition. Here, this first term is the first term squared. So you have x squared. The last term is the last term squared. So you have 25. Now, there is a middle term. That middle term is both of these multiplied. So 5 times x, which is just 5x. Now, what are my signs? There's a very easy way to do this, and it's called SOAP. It is the cleanest math you will ever hear about, and it's the cleanest math you'll ever use. SOAP, brought to you by math. Okay, now here's how that works. Remember I said this sign is the same. So it's the same as the original problem for the binomial. This sign is the same. This sign is the opposite. This is positive, this is negative. This sign is always positive. Same, opposite, always positive. That's pretty cool. Now, check this out. Let's assume that I'm looking at another problem. Let's assume that I'm looking at 64 m to the third minus 27 n to the third. Notice we're talking about a difference. These are perfect cubes, but we're talking about a difference. So there's one slight change. This is called a difference of cubes. And it works the same exact way as the sum of cubes. But the difference of cubes has a slightly different definition. So if I have x cubed minus y cubed, right? I have x minus y, x squared plus xy plus y squared. Again, the hard one is the binomial. So you have to ask yourself for that first term, what times what times what gives me that first term? What times what gives me that last term? And that is your hard part. Your signs are the same, the opposite, and always positive. Hey, the signs are soap. They're the same exact thing. Sum and difference of cubes. They're just opposite of each other. So 4 is the perfect cube of 64. So I have 4m, 3n. 3 is the perfect cube of 27. My sign is negative. So that is the hard one. What times what will give me 64m cubed? That's 4m. What times what gives me 27n cubed? That's 3n. What is my first term? It's the first term squared. 16m squared then. What is my last term? It's the last term squared. So that's 9n squared. What is my middle term? These two multiplied. So that will be 12mn. What are my signs? The same, opposite, always positive. That's it. So sum and difference of cubes are extremely easy, but you have to be able to identify the cubic values. So let's do another one. I have 8s cubed plus 216. Now those are perfect cubes, so and they are even, so you could technically do a GCF here. So what goes into both 8 and 216? I wonder. 2, obviously, right? If I put 2 in there, this becomes 4. This becomes, what, 108? They're still even. So what if I divide by another 2? That would be 2. That'd be 54. It's still even. What if I divided by another 2? That would be just s cubed. This would be 27. Still perfect cubes. So you can still use your GCF factoring. So we're going to factor out 8 because that is the common factor here. This is s cubed plus 27 once you factor that out. This is a sum of cubes still. So you did your GCF, you got that. It's not 4, it's not 3, it's 2 terms. And it is cubes, so you can use the sum of cubes here. That means you have 8 s plus 3, because you're creating that binomial first. The first term is this term squared. The last term is this term squared. The middle term is these two multiplied. Same, opposite, always positive. Boom. Mic drop, but it's a marker, and I need it, so I'm not dropping it. Okay, that being said, let's look at one more, and we will conclude this section. So you have 4x cubed minus 49x. 4x cubed minus 49x. Now, first and foremost, again, GCF. Do you have one? Yes. Both of these terms have an x. Pull it out. So you have 4x squared minus 49. Anything else? It's not 4 terms, it's not 3 terms, it's 2 terms. Does it fit any of the definitions I know? How about difference of squares? Because this looks like a perfect square, that looks like a perfect square. They are in a difference. Let's do it. So I have x, because that's still out here, and I'm going to factor. So the difference of perfect squares, this should be 2x and 7, 2x and 7, opposite signs. Boom. Does this factor down anymore? No. Leave it alone. So just to go back on everything we were saying, whenever you're looking at factoring, factoring follows a very precise process, if you will, a step-by-step process. And that's coming down to really to these 4 rules. Either 1, well, always 1, if you have a common factor, pull out the GCF. 2, if you're dealing with a 4-term polynomial, factor by grouping. 3, if you're looking at a 3-term polynomial, you have a couple options. You can use box, guess and check, or AC method. And if you're dealing with a 2-term polynomial or a binomial, look for the definitions for these 3, either difference of squares or sum and difference of cubes. Okay, guys, now the next little section is actually jumping into integrated factoring review. Now you have all of the answers for these factors on the second page, and they are right down here at the very bottom. I encourage you to go through and complete these exercises on your own. There will not be a separate video for these at this time. All right, guys, that concludes our section for today. I hope you have a great day and stay tuned. We've got another lecture coming right up.